Okay, so I'm gonna continue this GPU topic, and I'm gonna introduce Cupy, which is a library built for Python. It's a subset of things in NumPy with support for GPUs, for NVIDIA GPUs. So I uploaded to the repository that I shared yesterday this notebook, another several notebooks. So here first, I have the instructions on how to set up Cupy on Rusty. Now that you have been given access to one GPU, and so these are the instructions to set things up. So you can see that the first things are just making sure that you're using this fluid environment for the Python, then just loading the CUDA library. The one that I chose was this 11.0, and then you have to do a pip install of Cupy for that specific library, which would be this CUDA 11x. So if we continue with this, we can import now NumPy as NP, Cupy as CP, and we can check for available devices. So in this case, you can see that there's one device with here the available memory is 31 gigabytes from the 34 total. If there were more GPUs, you could use this command to choose between the several GPUs. In this case, we just have the 0, so we can allocate that one. And so we're going to start with allocating an array on the CPU and another one on the GPU. So you can see that the difference between those things is just using, yeah.
Sorry, do you want us to be doing this as you're talking?
Not necessarily. You can do that in the tutorial section later. And so, and then for the GPU using CP. And so we can, for instance, here do compute the mean value of an array on CPU and do the same thing now using, again, cp.mean for the GPU array. You get the same result. So CUDA has this Cupy library has its own functions to move memory from the CPU to the GPU. As Jim mentioned before, there is these physically different memories allocated for the CPU and available for the GPU. So you have to handle that somehow. So here, for instance, there's this function of Cupy to move something on the CPU to the GPU. And vice versa, there's something to move something from the GPU to the CPU. And the way to build code that is agnostic to the kind of array that you have is to read the model, for instance, here for this soft plus function. You can use this function to get what is the model of the array that you're feeding this function, and then use, so this XP is going to be a placeholder for either NumPy or Cupy. So you can give this function whatever you want. So for instance, here I'm feeding it with the CPU array. It's going to perform its operation, and I can do it also for the GPU one without any complaint. Where if I hadn't done that, for instance, if I had changed this thing to be always MP, and I perform this operation, well, actually, that's something that has changed recently, that it can be done. Before it couldn't. The only difference now, as I'm going to show later, is that the performance is a little bit slower in this case. But so you can retrieve, as I mentioned before, what is the module of these things. So for instance, for the GPU one, it's going to tell you that the module is Cupy, whereas for the CPU one, it's going to tell you that it is a NumPy one. So now we can move to timing. What is the benefit of actually using this Cupy thing? So here I have an example of making arrays on GPU and CPU for instance, first just 10 points, and making the same operation several times on either device, host or CPU. And then here you can see that the time that it takes on first on the CPU, then on the GPU, and what is the speed up. So you see that for something small like 10 elements, actually CPU is faster than GPU. And if we start moving to larger things, you see that, for instance, the time that it took for 10 points with the GPU is the same that it takes for this for 100. And this is because you're not saturating the GPU. You can still have more processors to be used, whereas the time that it takes from on the CPU is increasing. So we can keep this experiment, and we see that even with 1,000, the time for GPU doesn't change, where the one for CPU is increasing. So the speed up is getting now closer to 1. If we go to 10,000, then we see that it's the CPU, the GPU is still performing the same these operations on the same time. So they all fit on the GPU in one go. They can be done in all in parallel at the same time, whereas the CPU starts to get slower. And if we keep increasing this thing further, then we see that we start getting like more speed up. Still, the GPU is doing the performance, this operation at the same time for all those points. And then if we go to something like 10 million points, then which now it takes more time for the CPU to do. Then here you see that it's getting closer to 100, the factor of the speed up. And so here I have an example of things that you need to worry about with these things being allocated deep in different memory spaces. If you try to add up things that are on the CPU to the GPU, it's gonna tell you this kind of error. So you have to make sure that the things are on the same place in memory. So if I'm gonna add something to a GPU thing, I have to use these functions of Cupy to move things to the GPU so I can make this operation, and vice versa. If I want to do these things on the CPU, I have to move things from the GPU back to the CPU and then perform these kind of things. The other way that you can do this thing is create a data manager. So here I'm showing an example of an implementation done by Contan Wegner, which is a student at ETH. He did a really nice job doing this. And so this data manager, actually, you can allocate your arrays in this object, and the object is going to handle where things are going to, you can tell to switch all the things that are allocated in this manager either to the CPU or to the GPU. So for instance, here I create my data manager, and I start allocating things. For instance, this array X on my data manager, which is going to be a NumPy array. As you can see here, another one for Y. So if I can perform the operations of these things here, and it's gonna be on the CPU. If I ask for what is the module of these things, it's gonna tell me that they're on NumPy, so they're ready to be computed on the CPU. But I can switch things to the device and perform now the operation on the device here multiple times of this power of X, computing the time that it takes. And what I mentioned before, that you can now with newer versions do the same thing with NumPy, and it's just going to take a little bit slower to do it, but it's not going to give you an error. And so, for instance, another thing that you can do with this data manager is that you can actually tell it it can have a placeholder for NumPy or Cupy, so you can perform the operation with just write code that is agnostic in that sense, and perform the operation with the proper one, which for some reason was slower, but it should be the same thing as the previous one. And now, for instance, if you are running your code on a notebook and you are doing things on the GPU and you try to plot your whatever you are value you have computed, it's going to tell you, it's going to launch you an error. You have to, again, switch back to the, it's going to, right now it's on the GPU. So you have to switch things to the host. And now you can actually compute these kind of things. There are other things. So what I show you right now was a simple way of using the GPU with Cupy. There are other ways to get more benefit of using Cupy in Python. So you can actually define kernels in more of a CUDA way. Here are some examples of these things. So if you are acquainted with how to write CUDA kernels, you can do the same thing in Cupy and actually optimize whatever operation you're doing for the specific problem that you are solving. And now for some implementation, well, let's first start with this. So sorry to torture you again with the spectral difference method. Here I have an implementation in 2D of the code that we saw yesterday. And so you can go to this notebook and just here to show you what is now the kind of the geometry of the problem in 2D, where these are the solution points, the flux points now in X and in Y, and these are the control volume averages that we are updating. And again, we use the same Riemann solver between these elements. We have this object, this class, the SD simulator, that now has another dimension. So we have the same kind of things as done before, but now we have an extra component. So if we move to what are computing, for instance, moving from solution points to control volume averages, now you have to perform two operations, so you have to integrate in both directions, and to compute control and to move back from one to the other, you have to do the same, the inverse thing. I think, and now the dimensions of the array in this case there are 4 dimensions. So you have to, in order to plot them in 2D, you have to squash them to a 2D array. So there's here a function to do that, and a function to plot, for instance, the solution with this non-uniform geometry of the mesh, so that it looks something like this, which actually it's not. It can be misleading. It can tell you that the solution is not nice, but if you actually, you can make a function to use the same basis and integrate to some regular mesh. And so after you get your solution, you can do this kind of like regularization of your solution using the same polynomial approximation. And so here, for instance, you see that now it looks nice. So there's no visual effect due to the geometry of the mesh, which could be misleading, telling you that the solution is not smooth when it is. Some details of the other implementation to do the time integration, where you see now that we have both fluxes in X and in Y. And if we move to the actual algorithm to solve or perform the evolution of the method, you have here again, now we have to interpolate from solution points to flux points in X and from flux points in Y. And now you have 2 Riemann problems. You have to reconnect the elements at the interfaces in X and also at the interfaces here in Y. And then the update of your predictions has now 2 terms, flux in contribution in X and then contribution in Y. And the same thing for the final update. So here I perform one time step for this 6-order simulation. You can see that the solution moves a little bit to the right and up. And now a function to perform the time evolution up to a certain date, similar to what I showed yesterday. So I move the solution to the middle, which looks the same because of the periodicity of the sine wave being 1/2. And we can perform again an analysis of a study of what is the performance time of the method. You can see here that if I were to run this thing, it's going to take like the last case is going to take 36 seconds. I'm not going to try that. But we can do the same thing as before and check like what is the convergence of the method. Here seeing that it's exponential, so it goes with the power of the order used for the method. And if we now compare what is the cost to benefit, so the error against the time that it takes to perform those computations, you see that it's getting better than compared to 1G. So it is clearly better to go to high order compared to low order to achieve a certain error in your computation. And you see here that the increase in time by doubling the resolution, it goes towards 8, which is given by the increase in size. So we are increasing in X and Y, doubling the resolution. So it's a factor of 4, and we are performing 2 more time steps to reach a given date, so that hence the factor 8. And now here, for instance, the trend of increasing the resolution, you can see that it goes to this line is n to the cube, so that factor I was mentioning. And so I continue with a comparison for a given number of degrees of freedom with increasing order, so second, fourth, eighth order, advecting a sine wave. Same exercise as before, showing that going to high order, even with the same number of degrees of freedom, it's better. You do see here that it's more expensive, 8 times more expensive to perform this computation than this one. And if we expand this to go to 100 laps for the domain, you see that this is almost gone, the solution at second order. And we can do, again, this exercise but now for discontinuous solutions like the square signal. And here I'm not going to run. You can see here that the time that it takes to perform these computations. So where I'm going to the extreme and showing you, for instance, in this extreme case, order 64 for just one element, and it's being advected. So that one is the one that takes like a really long time. But now we can move to the same script, the same notebook, but now I'm gonna make use of these. Sorry. Now let's restart. And I'm gonna make use of, I'm gonna check for devices. I'm gonna make use of Cupy and of this data manager. So we have the same things, and the only things that I'm gonna change is that whatever things I know that are gonna be used on the GPU to make the evolution of my solution, I'm gonna allocate them using the data manager. So for instance, here, I know that I'm gonna be using these matrices to compute interpolations. So I allocate these things with my data manager. For instance, my initial conditions, I know that they're not gonna be used in the evolution, so I allocate them not on the data manager, but I allocate the things that I'm gonna be using, like the velocity and the solution that is gonna be updated. I allocate that on the data manager. And so we can proceed, and so we can check that it works on the initialization. And then on the other part, I know that, for instance, this inverse matrix to compute, to go from one prediction to the next one is going to be used in the evolution. So I allocate it on the data manager. Also the solutions, these time slices that I'm going to be predicting are going to be used in the evolution. So data manager, the fluxes also. So those are the changes that I do. And then when I perform the evolution, I name this XP, which is a placeholder for whatever the data manager is choosing at the moment, if it's allocated on the CPU or the GPU. And I use that to perform these kind of NumPy, Cupy operations, for instance, this Einstein summation. So those are the only things that I change in this thing. I replace all those MP that I had before with this XP, and making sure that I'm using the arrays that are on the data manager. And so here it performed one time step before doing, actually that was done on the CPU. Now I do my function for the time evolution, and here is when I'm going to call this function to switch, written on the data manager, to switch the location to the device. I perform the execution of my evolution, and after finishing the computations on the GPU, I can ask that to copy back my solution to the host, so I can actually plot my solution, which is what I'm going to show you here. So now it was performed on the GPU, and if we go and make the same kind of experiment that I was showing you before, where here I'm going to, for instance, I can run this thing and show you in the meantime what was done here. Where was that? Sorry. So here you can see that I went up to 16 elements with 8 order, and it took 36 seconds. So in this case, I actually decided to go further than that and actually go to 4 times more elements, and maybe it's going to take too long. Well, we can move forward, like in checking again that the solution is correct, as is reproducing what we had before on just the CPU. So here again showing the convergence of the method, and now you can see that it was extended. So previously I was just showing up to just 3 points, so I increased the resolution 2 more times, and yeah, it's still running. So we can, and well, I don't know what happened there. That was a fluke, but you can see here that it's even more drastic, the kind of like the gain of the time that it takes to the error that you obtain with the method. And yeah, I don't know what happened there. Previously it was all linear. So if I was showing the previous results for this thing, I was seeing just a linear increase in time by doubling the number of elements. So linear instead of cubic, which was the results for CPU. Yeah, maybe we can rerun that thing now. Oh, still running. We can book. And now I perform the evolution of the sine wave, and using more degrees of freedom. Now the thing with using Cupy is that it's going to be more expensive, as you saw before, for a small number of elements. And here we are limited by the amount of time steps that we do, that we cannot parallelize. those things are serialized. But if we increase the resolution, so we go to the example of the square, of the square, I make the same experiment, and you see that here, where it used to be 600 plus seconds, it's now 31 seconds. And I made a study that I'm not going to run here, but you can run later by yourself with the notebook. I time what is the execution for first making simulations on the GPU for increasing order. So going second, fourth, 8, and 16 order. And I performed the same thing where here you can see that the most expensive solution computation was something like, well, here 2 seconds. Whereas if I were to do that thing on the CPU, it's gonna go to 300 seconds. So if I plot what is a speed up, now I see this saturation of getting to 100 times, well, here almost 200, which was mentioned by Jim. Of course, comparing one GPU against one process, but we're doing something that it's simple. Whereas in Python, if you were to vectorize a thing, you would have to do something more convoluted, like using NumPy or something. So this is just acceleration, like free acceleration that you get just by using this Cupy thing. And at the end, for instance, what I was seeing here with other results is that if I were to increase the resolution for different number of for a different number of degrees of freedom, I would see that the cost of going the cost of increasing the order at a constant number of degrees of freedom was just doubling the cost, where the cost should be way higher than that for a lot of points. And then we see that if we increase that further, we reach saturation of the GPU, and it starts going to something more expected, like 8 times more time. And so I think I went too fast, but that's all that I have to share right now. Questions?